In today's video, we'll try to understand the concept behind the flux, the quantity which we call flux, and then what is electric flux, and then we'll talk about what is Gauss Law, how this relates with the charge enclosed and the whole concept that is there. Well, in a very general sense, let us understand in a generalized sense, what this word flux means. So, we'll try to understand this term which is known as flux, and we'll try to understand this with an example. Suppose we imagine a laminar flow of air stream, right? Air flow. And when we are talking of air flow, there's no turbulence, it's laminar flow, then we associate a quantity which is the velocity. It is moving with velocity v. And then suppose there is some hypothetical surface here, okay, and let this airflow crosses this area. There's a hypothetical surface or area that we have considered a loop in a form of a square, and we are interested that when these airflows strikes or it comes near it, it passes through this area in this direction. All right. So let's see how the quantities are related. Well, before we move ahead, let's talk about one more very interesting aspect when we talk of a loop, area loop. So we have heard about this quantity area. But do we know what is area vector? What is area vector? We know area, the very quantity area, is describing a surface, right? It is giving an idea of a surface, and it does not require a direction, right? But we are trying to figure out that this area is facing some direction, and there comes this quantity area vector. Suppose we imagine a square or any rectangle of this kind, and we associate some references. Suppose this is lying on a plane, and this marks x-axis, this marks y-axis. So this is facing in this positive x and y plane, this is xy plane, right? And here we know that we associate this unit vector along this x-axis as I cap, and we associated j cap vector, a unit vector along y-axis. And we imagine this is square, this surface, to be lying on this plane. And now we are trying to figure out that this is having a face, and that face is showing up in the direction which is perpendicular to this xy plane. So any direction which is perpendicular to the xy plane, so if we want to make a three-dimensional coordinate axis, we can associate this with z, and we know these all three axes are mutually perpendicular. मतलब अगर ये x axis के along इसका length है, y axis के along इसका breadth है, suppose, then here if we imagine that this is facing towards this side, and we associated another vector here, unit vector k. So the area vector that we are trying to conceptualize is the area vector has this direction along this z-axis along is k. So if I take an example, suppose I take a book here. Here's a book, and this is describing the length of it along I cap. This is breadth j cap. So this is which is coming towards you, right? This is k cap. This face which is facing towards you, this is in xy, positive xy plane. It is protruding towards you. That direction is the area vector direction. So the area, although it's scalar, when we talk of area vector, this is actually showing up the face of it, and this is along this direction. So if I take this to be positive, this to be positive plane, this is protruding towards in the same direction as we have the direction of the velocity. So we have the area vector here, which this airstream, airflow having velocity v is flowing across it, through it, and this area vector is in line with this velocity direction, this direction of this airflow. This is where the two quantities are involved here when we are trying to figure out that this airflow airstream is passing through this loop, this a rectangular loop, suppose a rectangular loop, and the direction of the velocity is same as the direction of the area vector, and the area vector is described in this way. Well, now if I want to ask you, say for small delta time t, what is the volume flow rate? So let's now understand this relation, and we are interested that this volume of air which is flowing through this loop means along the area vector, and we are interested in this quantity which is volume flow rate. Mathematically, if we try to conceptualize this, we'll come on, when we talk of rate, then time comes into picture, right? Volume per unit time. So basically with volume flow rate, we are trying to figure out what is the volume of flow of air per unit time, right? Per unit time. This is what we are trying to get an equation, a mathematical value for this, given these two quantities. Now, if we imagine the delta time to be t, so in the time interval delta time t, right? We know this volume. What is this volume? This area, right? This area, whatever we have the value area. If I multiply the volume, the area with the distances it traveled in this time interval. So the distance in delta time t, the distance traveled, right? The distance traveled with this given quantity would be what? We know the velocity is v, and when we multiply the velocity with the time interval, we get the distance traveled. Area multiplied by the distance traveled is going to give you volume. So therefore, volume of the air flowing in delta time t, right? So this comes out to be volume would be v delta time t times a, this times a. All right, so this is going to give you the relation between the area and the volume, but we want to find volume per unit time. So from here we can write therefore volume per unit time. So in delta time t we get this volume, therefore volume per unit time is going to be equal to, so this is going to be equal to v times delta t times a divided by delta time t, and we get delta time cancel, therefore volume flow rate is equal to v times a. So this is where the relation comes, that the volume flow rate of the air stream that we are talking about, the airflow, with this combination gives you the volume flow rate, which is volume velocity times the area. So we are able to establish this relation. So we have just tried to figure out a very basic definition at this point in time. We tried to figure out, let me walk you through again. We tried to conceptualize that there's a laminar air flow having the velocity v. And we are interested to find that this air flow is passing through this hypothetical rectangular surface, passing through, which means that the velocity direction and the area vector direction is same, right? So if it is passing through this loop, then what is the volume flow rate of this airflow? The equation that we want to find is volume flow rate is equal to what with the given velocity and the given area of the loop. And we conceptualize, suppose in delta time t, the distance traveled would be v times delta t. Now if the distance traveled is this, if volume we are talking about, we already know the area. When we multiply the area with the distance, we'll get volume. So now we know the volume of air flowing through that loop in delta time t is velocity times delta time t times a. So we are interested to find what is the volume flow rate, that is volume of flow of air per unit time. So in 1 unit time, what is the volume of flow of air through this loop, right? So per unit time, we'll have to divide with delta time t, and when we divided, we get these two quantities cancelled, and now we are getting a relation that is showing that volume flow rate is equal to velocity times area, the given area of the loop. This is the relation that we got. Well, having understood this, now let's try to get deep into it and try to understand what this makes sense, what sense it gives apart from this volume per unit time, the flow of the air per unit time. Apart from this, what more sense it gives with this relation? So it is showing you that this velocity v and this area that is there, at every point in time, at that particular instant, any point in time, through this area, and this area is addition of small areas, right? Small areas, and through all those small areas, this velocity is same, constant. Through all the areas small, if I divide this rectangular area, big A, into small chunks, small squares that fits into it, through that small squares, the velocity is same, VA. All along this, through the loop, we find the velocity is all along the same. And that is what we conceptualize as velocity field, right? Which means that the velocity field is in this area which is enclosed by this loop. There is a velocity field that exists, and this velocity field has a relation with this loop when we talk of this is passing through it. So this volume flow rate that we were talking about, right? Volume flow rate that we were talking about is giving you a sense here that this is a catchment area. And this catchment area that we are talking of is the area A, and there's a velocity field. And this velocity is all along, but the catchment area is this. So it gives the sense of this volume flow rate is basically, that is what we are talking of, flux. So this velocity, we are getting velocity field there, and this flux, when we are talking of this velocity field, the flux of what? Of this velocity field, when we have a specific catchment area, it gives you a sense of flux. So basically this flux, when we are talking of here in this context, the air having velocity v is VA. Now mind you, here we have taken a very specific condition that this is in the direction of A. Now what if the component, suppose if we take the other extremes, when we talk of any extreme which is not flowing through, but the air is getting, the air is flowing in this direction. The air is flowing in the direction of, perpendicular to the area vector. Then we are saying that this airflow is not passing through it, right? Is not passing through it. So one situation is all of the air is passing through it when it is in the direction of area vector. And if the airflow is in the direction perpendicular to the area vector, then none of the air component or the air velocity, particles or air is flowing through it. So with these two extreme situations, wherein all of those air which is coming through, striking this area, is getting through, is a situation when V is perpendicular, when V velocity is in direction with the area vector. The other situation is when we have a velocity in perpendicular direction to the area vector, none of the air is flowing through it. So with these two extremes, let's take a generalized position. Suppose if I redraw this situation, if I redraw this here, and now I made the airflow to be in between these two extreme situations, wherein all of those are not passing through and none of those are passing through. Some are passing through, some are not. What could be the situation? It could be that this airflow direction, the velocity that we are trying to make, is making an angle. Right now, this is in this direction. It is passing through in this direction. So now if I draw the corresponding, so this is the velocity direction. And now we'll draw the area vector. So suppose I take this as reference, area vector is always in this direction. So now we see that this is making an angle theta. If it makes an angle theta, velocity vector makes an angle theta with the area vector, then when we are talking of this flux, then what we actually mean in this generalized situation? In this situation, we mean that this will have two components, right? If I draw my references, this velocity vector has two components. One would be along area vector, the other would be along perpendicular to the area vector. And when we know that the one which is perpendicular to the area vector is not passing through. So what is passing through? Passing through is that component of V which is in parallel or in direction with A, which means that if I drop a perpendicular from this velocity vector to the area vector, this component of velocity which is in this direction, and this is making an angle theta. So if I resolve this velocity vector V and try to find what is that component which is along A, and with A it is making theta, and we know by geometry, we know by our understanding of resolution of vector that this is going to be then V cos theta. This component V cos theta is the component of that velocity which is in the direction of A. So now if I want to find the direction, the equation for flux, right? And again with the flux we mean the volume flow rate. With the flux we mean the volume flow rate. So we multiply V. Now it's not V, now it is V cos theta, and then we have here A. So we have this A V cos theta. So what do we know? We know that this flux is basically, we are trying to say that the magnitude of A magnitude of vector, velocity vector v cos theta is what is flux now. A very generalized situation. It's all depending upon the angle theta. If I make this angle theta 0, it's going to be the maximum AVA. If I make this 90 degrees, we know cos 90 is 0. Everything 0 gets 0, so which means that flux is 0. So from our vector understanding, we know this flux is V dot A. So it's a dot product, it's a scalar product that we are talking of here, and we get now a very deep understanding of flux, that this is actually a dot product of velocity and area vector. And this flux, just to remind you again, we are talking of this flux, which essentially means volume flow rate. Great. So take down this concept, try to understand this, and then from here, with the generalized definition and the generalized concept of flux, we'll move on to understand what is then electric flux. Similarly, when you would study magnetic field, there you will come across a quantity, magnetic flux. The concept of flux remains same. It depends upon what quantity we attach it, and then we have a equation describing the entire situation. Good. So take it down, and then now we'll try to understand what is then electric flux. Well, okay. So in general, we have understood what is flux. Now let's discuss again. If you remember, we talked about velocity field, right? Velocity field. So when we are talking of velocity field, we are getting a general equation for flux. But what if we talk of, instead of V, we talk of electric field? So this V that we are talking about, we are talking about this flux in the context of the velocity field. What if I take the same analogy, draw the same analogy in the context of electric field, and we know instead of airflow, now if I take electric field here, we take electric field, and now we try to conceptualize this electric field is what is that which is passing through this area which is there, and we already have this area vector defined as A. So we'll, with this same understanding of flux, we'll then just modify this to electric flux, and this electric flux would become here E dot area vector. So the electric flux is E dot area vector in total. All right? Well, now in differential form, as in velocity field, if you remember, I told you that the velocity is constant. If I divide this square into small bit of squares, infinitesimal squares if you take, in that small infinitesimal small area, the velocity is same. The velocity is same across all the surface which is described by this loop, and that is why we were calling it velocity field. Now we have an electric field in the same situation. Electric field, and when we divide this into small bits of area, suppose in a differential form, when we divide this, we'll get electric field in that ways. So in the differential form, we'll get the electric flux. A would be dA in differential form, and here we'll designate this with this notation, which is phi, which is electric flux, differential elemental electric flux. If I want to get an equation, I'll get electric field is constant, E dot differential area. So if I want to find what is the net flux, net electric flux from this equation, we'll have to integrate this. So this net phi E net would be equal to integral of dE d phi, right? We have designated this notation, but over what? Over this closed surface. So we'll encircle it here. So this will tell you, give an idea that you are integrating in the closed surface, and this comes out to be here also you will be performing integration over a closed surface, which is E dot dA. This is what we get, the final equation. So basically this phi net, which is in the context of electric field, we are getting is equal to integration over closed surface E dot dA. This is where we get the relation of electric flux with electric field and differential area. Extremely important concept to understand. What do we mean by flux and why this quantity is so important? Well, now having understood this electric field, we'll now try to understand from Carl Friedrich Gauss Law, what is the idea behind when we talk of Gaussian surface, when we talk of the relation between the enclosed charge, and when we talk of the idea behind in evaluating this equation to solve many of the problems. So watch in the next video, we'll derive the equation Gauss law, and then we'll try to understand, and then we'll apply the Gauss law to different problems to figure out what is the net electric field. Well, thank you.